So to end our introduction to torque, I'm going back to this weird L-shaped thing that I cut out before. Right, so a couple of things geometry-wise. Let's say this is 20 centimeters. Let's say this is 20 centimeters. Let's say the whole length here was 1 meter, and let's say the whole length here was 80 centimeters, just to, or actually let's do 100 centimeters just to make this consistent. And we said that we were going to force this thing to constrain its rotation about that point. So I'm going to hold that point down as everything happens. And so let's exert a whole bunch of forces on this, or virtual forces. Okay, and let's do one more here. All right, so let's say all of our forces have a magnitude of 100 newtons. So here we go. What I want to do is find all the torques. Well, first things first, what I'm going to do would be exactly what I have here, which is a free body diagram. Super important free body diagram. Notice also in my free body diagram, I have all the important distances labeled near the diagram, but not on the diagram. It can be super critical for our free body diagrams. The next most important thing is I have written in where the axis of rotation is. You cannot calculate a torque if you don't know where the axis of rotation is. So that's critical there. The next thing I'm going to do setup-wise is, as we always do, axes and declarations. Here, I'm not concerned about translation because that thing's constrained. We'll talk about that later. What I am concerned about is rotation. So let's just call clockwise positive for sake of argument. Now you could call clockwise positive, counterclockwise positive, it's your choice. So here we go. We're going to do and find the magnitude of each of these torques. Now I'm going to stop writing these magnitude signs in a couple of minutes, but just for the first couple, we'll draw them in. So I know that that's going to be the magnitude of force 1 times the lever arm distance for force 1. We're not going to go into the RF sine theta thing if we don't need to. And here it's actually pretty simple, so we're going to leave it like this. So here we go. What's the magnitude of the force? It's 100 newtons. What's the magnitude of the lever arm distance? Well, F1, if I look at it, its line of action is like this because it's a horizontal force. Therefore, L perpendicular is going to be this much here because that's the shortest distance to the pivot. Now, so what's that? 1 meter. So what does that give us? That gives us 100 meter newtons or Newton meters. Now, I know you're going to want to think Newton meter, joule, but we're not going to do that. Sidebar here. Torque is R cross F. Work is F dot delta S. So here it looks like you get newtons times meters and Newton times meters, but actually here this is a Newton dot a meter and this is a meter cross a Newton. Now we're not going to get all technical and write in that cross every time, but a joule is actually defined as a Newton dot a meter, not a meter cross a Newton. So we're going to leave it in terms of meter Newton so that we don't accidentally make that a joule. Now, what direction is that? Well, if I put my finger there and I exert a force that way, you can see, and I'm actually going to physically do it, the paper rotates clockwise. So that's going to be a positive 100 meter Newton. All right, so let's do the next one. Torque 2. Force 2, lever arm 2, and what do we got here? Oh, well, this is a vertical force, and its line of action goes through the pivot, so although this is 100 newtons, its lever arm distance is 0. This would not cause a torque. Next, torque 3. Force, lever arm distance 3. So once again, 100 newtons, and then this thing, here is the line of action. or rather, yeah, and here it would be the lever arm distance, a horizontal distance. So that's going to be 0.2 meters. So that's going to be 20 meter newtons. Now, if I look at how that's going to rotate it, boom, that would cause it to go counterclockwise or negative. So torque 4. What do I got there? Force 4, lever arm distance 4, 100 newtons times, if we look, there is the line of action, and so that's another 0.2 meters, and so that's 20 meter newtons, and this would cause a positive torque. Torque 5, force 5, lever arm distance 5, so 100 newtons, and so if I look at that, there's my line of action, there's my perpendicular distance, 0.8 meters, so that's 80 meter newtons. Now, is that going to be positive or negative? Well, if we look at that, that would cause the system to rotate counterclockwise. All right, and so now let's move there. I want to make sure that my picture is still in line. Okay, and then torque 6. Darn. So what I'm going to do here is I'm going to split it up into components. Now, if you notice when I split up into components, I no longer make a triangle. And that's super important, folks, because where the force acts is critical, right? If I put F6x here, it wouldn't look like its line of action goes through the pivot, and that's super important that it does go through the pivot. Because here, the torque due to 6x is going to equal 0 because L perpendicular 6x is 0. But the torque due to 6y is going to equal the force of 6y times L perpendicular 6y. And what's that going to be? Well, for 6y, if we look at that, that's going to be 100 newtons times sine of 45, and then the lever arm distance here is 0.8 meters. So what's that? That's 70.7, I think, newtons times 0.8 meters, and so 6, 5, right? Let's just do that. Move that over. Is going to be that, or something along the lines that, Newton meters. And if we look at that, what direction is that going to make it go? That's going to make it go counterclockwise. Okay? And so that's how we can use line of actions and lever arm distances to find torques. Now, there are some problems we're doing are F sine theta is easier, and we'll see those in the textbook in an assignment that I'm going to ask you to do. One last thing I can talk about for today is going to be the concept of net torque. Net torque is just simply the sum of all the torques. So in this case, if positive is clockwise, that would be plus torque 1, and then torque 2 would not even be in this because it zeroes out, so I'm just going to do that, minus torque 3, plus torque 4, minus torque 5, and then minus torque 6 based on the way those happens. Don't double up on the negatives here. 100 meter newtons minus 20 meter newtons plus 20 meter newtons minus 80 meter newtons minus 56.56 meter newtons. And looking at that, it looks like I get something like a negative, I get a negative 36.56 meter newtons. So what's the implication of that? Well, that means there's a net torque counterclockwise. So if this thing's initial angular velocity was 0, after a bunch of time, this thing is going to begin to rotate and speed up going counterclockwise. And so if you've guessed it, there's going to be a link to alpha here, but I want to get us comfortable with the concept of torque before we put this into Newton's second law for rotations, which we will see.